All right, this is episode 1 of Quantum Observer. Is reality the greatest optical illusion? What if the universe is a computer and we're finally learning its code? So we talk about quantum mechanics like it's abstract, but it's actually not. It's actually the foundation of a technology that is about to completely rewrite how we process information, how we make decisions, and how we even simulate reality. I'm Jesse Welch, and for legal purposes, I have to tell you, I'm not in Kansas right now. This, however, is the Quantum Observer. This is where we decode the absurd principles of quantum physics, and we try to translate that logic into quantum computing, the logic of quantum computing. And we try to explore how that's going to reshape industries and how it's going to change markets. And also, it's going to change how our lives are currently built, which is on classical assumptions. Today, we're just going to go over some of the core principles and concepts of quantum physics that you'll need to understand in order to know what that means for this next huge leap in technology. So we're going to explore what that means for quantum computing, what it means for computing power, business strategy, and even the future of problem solving itself. Here's the first thing they don't tell you in high school. Reality itself isn't actually what it looks like. So the solid world that you think that you're standing on, like the one made of matter, weight, and reason, it's actually mostly an illusion. It's a remarkably stable illusion, yes, but it's still an illusion. You see, at an atomic level, that chair beneath you, the chair beneath me, it's actually 99.9999% empty space. The atoms that make it up, see, they feel solid, but they aren't actually touching each other at all. They're actually held apart by electromagnetic fields. These tiny zones of repulsion that give you the sensation of contact. So when you sit down, you're actually not resting on matter exactly. You're actually hovering over organized probabilities. It's kind of like a handshake of forces that only seem solid because the particles are all playing along, if that makes sense. See, that's one of the really big shifts in quantum physics and what it forces on us, that the universe is not a construction of objects. It's a network of interactions. And see, these interactions, they depend on one key thing, whether they're being observed or whether they're being measured. In physics, it's actually called the observer effect. And I'm going to do an entire episode on the observer effect later because it's really cool. Now, it sounds really mystical. And it's actually partly what we named this show after. But it's actually entirely mechanical. See, to know where an electron is, you have to bounce a photon off of it. A little bit of an oversimplification. But that photon gives the electron a tiny kick. It's enough to change its motion. So the very act of measuring it actually alters what you're trying to measure. The simplest way that I understand it is, in order to observe a photon, a little particle of light, not exactly a particle, it acts like a wave sometimes too, but in order to observe a photon, you have to absorb the photon. Therefore, you alter the photon. See, every detector, every sensor, every beam of light that we use to see the universe is not separate. It's actually part of the system that it's measuring. It's Gonzo style, right? It's not philosophy, it's physics. And it's the principle that quantum computing is entirely built on. What does observation really mean? In a classical computer, information is stored on bits. It's binary. It's either yes or no, on or off, 1 or 0, right? But in a quantum computer, information is actually stored in these things called qubits, right? Quantum bits and they behave kind of like tiny particles of light. See, each qubit exists in a superposition of states. It's kind of like a probability cloud. I'll do a whole episode on superposition later. Now, what that means is it can represent many values simultaneously. It can hold multiple possibilities until it's measured. And then, once it's measured, the qubit collapses into a single result. Does that sound familiar? Hopefully. See, this actually follows the entire same rule of the rest of the universe. Quantum computing doesn't work despite uncertainty. It actually works because of it. Every single qubit is like a miniature version of the observer effect. It says, until you look, I hold all possibilities. And then once you look, that's when I decide. And that right there is the foundation of an entirely new logic, like a new way of thinking. It's one that treats ambiguity not as a bug, but as a feature. Why this matters to you. So let's bring this out of the lab and into the boardroom. Why should anyone outside of physics actually care that electrons have commitment issues? Well, because this shift in thinking changes what's computable. So classical computers, they move through problems one state at a time. Even when they do it at extremely fast speed, like AI is still doing problems one at a time. Quantum computers, by contrast, they can actually explore multiple outcomes in parallel. So imagine simulating every single molecular configuration for a new drug all at once instead of one by one. Imagine solving logistics or portfolio optimization problems that would take a classical computer longer than the age of the universe itself. Imagine doing that in a few days, or a few hours, or maybe even a few seconds. Imagine cracking encryption, not through brute force, but through quantum pattern recognition, harnessing the probability landscape itself. See, this is why quantum computing matters, especially if you have a Bitcoin wallet. It's not just faster computing. It's a completely different way of computing altogether. It's one that mirrors how the universe itself processes information. Quantum computers, they don't just calculate outcomes. They actually navigate possibilities. They navigate probabilities. And that's what makes them so powerful. We're going to get into things like magnitude and phase a little later. But for now, that's the concept to really keep in mind of how this works. The massive amount of probabilities are actually what makes it powerful instead of what makes classical computing's major hurdles. So, this isn't just about technology though, it's about perspective. You see, observation has always shaped reality, even in the human world. You know, a biologist alters a cell by observing it, by shining that light on it, adding a little too much heat to it, right? A therapist changes the story by listening and just by being there and being present while the story is being told. Probably the biggest example, a person changes their behavior when they're being seen or when they have a camera on them. See, the 20th century completely shattered the illusion of neutrality. We don't just record the world, we interact with it. We have to, and in doing so, we influence it because we're part of the world. That's sort of like the human parallel to quantum computing. It's not really about control, it's actually about engagement. Even the measurement is engagement. There is no passive observation. Observation is participation. About understanding that systems, physical, digital, social, they evolve through interaction. And when we build quantum computers, we're not inventing something alien. It feels really alien, but it's actually one of the most natural things we could possibly build. We are finally engineering machines that think in the same way that the universe does. It thinks through probability. It thinks through entanglement, another buzzword, and it thinks through choice. So, the next time somebody says to you, quantum computing, I've heard of that. That's spooky science magic. I doubt anyone will say that to you, by the way, but someone might, maybe your uncle. you can just smile and say, no, it's actually the most honest computing model that we've ever built. Because in a world where everything exists as probabilities until it's observed, computation becomes participation. And that's one of the biggest steps in understanding quantum computing, is that you can't just compute, you can't just experiment without actually being part of the system. It's realizing that. And it's also realizing that reality is not a thing that you stand on necessarily. It's more like a wave that you ride. So we'll put this to the test at some point with the experiment that started it all. I won't actually do the experiment. I'll just try to explain it in a way that's pretty easy to understand. It's actually the one that made some physicists question whether reality even exists when no one's looking. All right, so the double slit experiment. This is really cool. It's the universe playing coy. So imagine this. You are in a quiet physics lab. You're actually a physicist. And you have a light source. And you have a wall with these two narrow slits. And behind it, there's this screen. And it records whatever gets through. So you shine a light at the slits. You're expecting two bright lines on the screen, right? You're expecting the light's going to go through and hit that screen. Instead, what you actually end up seeing is a striped pattern of light and dark bands, right? You see what's called a wave interference pattern. Now, waves overlapping, they're canceling each other out, they're reinforcing. It looks like ripples in a pond. It looked like very much like ripples in a pond. Now, easy, great, all right. I thought that light was going to shoot through like particles, but turns out light behaves like a wave. Done, case closed, wrap it up. Until you dim the light, you send the photon through one at a time. Now, in this situation, you'd expect each photon to pick a slit, right? Left or right. But actually, no. Over time, the same interference pattern appears. Each photon seems to interfere with itself, like as if somehow it went through both slits simultaneously. That's actually really what it looked like. So what these physicists did, they added a detector, right? Something to watch which slit it passes through. And then suddenly the interference pattern disappeared. So the moment that you look, the wave collapses into a particle. So actually, the very act of observing the experiment changed the outcome. This blew people's mind. They didn't understand it for decades. See, when unobserved, each photon explores all possible paths. When it's measured, it finally commits to one. This is not psychology. It sounds like it, but it's not. These photons are not sentient. As far as we know, it's actually physics. And it's repeatable with electrons, atoms, even like 60 atom carbon molecules. See, at a quantum scale, matter behaves as probabilities until interaction locks one of those probabilities in. From waves to qubits. This right here, this is the heart of quantum computing. A classical bit it's definite. It's 0 or 1. It's binary. A qubit, like our photon, it exists in a superposition. There's that word again. Remember it. Many possibilities at once. While the qubit remains unmeasured, it behaves like a wave function. It's a map of probabilities that can interfere with itself. This is hard to understand. This is actually one of the things that I hate about the coin flip analogy, because probabilities always have to add up to 100% with the coin flip, but these probabilities can actually work against each other. Quantum algorithms now take advantage of that interference. See, they choreograph qubits the way that we choreograph the lights through the slits. And they combine, they cancel, they amplify paths until only the right answer survives. See, when we finally measure the qubits, the wave function collapses and the computer outputs a single result. A classical answer distilled from quantum possibility. That's the breakthrough. These classical computers, they test options one after another, even when they're doing it really, really fast. Quantum computers, They let all the possibilities collaborate and compute in parallel. So infinitely many times faster. The double slit experiment is not just a curiosity. It's actually what became a blueprint for computation. So, programming interference. Here's where it leaves the lab. I said this earlier, drug discovery. Drug discovery is going to be one of the biggest and most revolutionized techniques, and just pharmaceuticals in general. All medicine is going to be massively impacted by this. Imagine testing billions of molecular arrangements simultaneously to find the one that binds. Portfolio optimization. Anytime we think we can make money with something, we're going to apply it to portfolio optimization. But imagine evaluating every market scenario all at once and not one back test at a time, especially routing logistics, climate modeling, AI training, all the same pattern. Quantum algorithms program interference the way that composers score music, kind of. See, some paths cancel noise, others reinforce the melody. And the final measurement, the note that we hear, is the optimized solution. So it's not science fiction, it's like engineering the math of probability into the hardware itself. And if your business or your field wrestles with like too many possibilities, too many variables to brute force, quantum computing in a few years might be your competitive edge. So the wider implications of this, let's call it the art of delayed commitment. The lesson hidden in the experiment is actually timing. You see, in quantum mechanics and in quantum computing, you don't rush the measurement. In fact, one of the things that we're trying to do is make the actual measurement and the decision or the outcome come slower, right? If you collapse too early, you lose information. We'll talk about quantum error correction and information leaking and stuff like that. But if you wait long enough, if you wait too long, the system's natural not if you wait too long, but if you wait long enough, the system's natural interference refines the results for you. So waiting it's not physics, it's actually a strategy, right? Let possibilities interact before you decide. Shape the landscape instead of forcing an answer. Quantum logic teaches us a kind of new version of patience, right? It's not real patience because you can only currently have these things in superposition states and for like fractions of a second. But it's the wisdom of delayed commitment. The architecture of possibility. Let's think about this like zooming out. For centuries, we treated reality as binary. It's a yes or a no, on or off, 0 or 1. Quantum physics revealed that it's actually probabilistic. It's a negotiation that's waiting for measurement. And quantum computing turns that revelation into architecture that we use. And it sounds like philosophical weirdness. And at one point it was. And there is still a lot of philosophical ridiculousness with quantum computing. But now that's actually being turned into technical design. What used to be a wave function collapsing is now actually a business model resolving. So yes, the universe might be the greatest optical illusion that has ever been staged, but we're finally learning how the trick works. And that's what's exciting about quantum computing. So maybe one of these episodes we'll talk about if everything is quantum, why doesn't your coffee mug split into infinite versions of itself every morning? The answer to that is decoherence. I'll do a whole episode on that, probably not a super long one, but it's kind of why the world stays put long enough for you to finish your drink. So here's where we land at the end of this episode, why I'm excited about this technology. Reality isn't solid. It's statistical. Everything you see from the chair beneath you to the stars above you, it's actually just a system of possibilities that only settles into place when it interacts and when it's measured and when it's observed. That's not philosophy anymore. That was, there's beautiful philosophy around it, wonderful analogies, but this is actually not philosophy. This is architecture. This is physics and science. This is how the universe processes information. Quantum computing does not fight that weirdness. It builds on it. And hopefully it gets rid of some of the ridiculous gurus talking about quantum along the way. It uses superposition, interference, and collapse, not as metaphors, but as tools. It doesn't compute in spite of uncertainty. It computes with it. A qubit is what happens when the universe itself becomes the logic gate. And that's what makes this moment so extraordinary, this moment in time. For the first time in human history, we're not just observing the laws of nature. We're not just working with them. We're actually engineering the laws of nature. We're engineering with them. We're building machines that operate by the same rules that reality does. Machines that don't guess the future, but they actually entangle with it. So if you do hear people talking about, or if you hear people say that quantum computers will change everything, they are not exaggerating. I'm not saying that quantum computers will replace your tabletop laptop or anything like that, because those things, they need to be super cold, at least with current technology. But they will change what's possible to know. They'll change what's possible to be computed, because in a quantum machine, the question and the answer exist together until you measure it. So that's the real observer effect. It's not mystical, it's just mechanical, but we finally are able to engineer those mechanics. But it is a deeply, deeply human thing, because to compute, like to live, is to choose one path out of many possibilities. So I'm Jesse Welch. Thank you for watching this, if you did. This is the Quantum Observer, where we try to decode the very, very strange world of quantum computing and the logic of the universe. Try to translate that into something that we can all understand and hopefully inspire a few people, maybe even to start looking to work in this field, and figure out what happens also when the act of knowing becomes a form of creation. I do get a little philosophical with this because I'm so excited about it, but this is rooted in hard physics and hard technology. Next time, we're going to explore probably a little bit about superposition. I think after the observer effect, that's probably the most important concept to understand. Thank you guys for watching. If you did enjoy this, like, subscribe. I'm on TikTok, we're on YouTube, we're probably on Instagram at this point. We've got a website. There will be a newsletter coming. I'll give you weekly news or maybe bi-weekly news, big advances in the industry, and let you know who the major players are and what they're doing. And maybe if people like me enough, I'll even throw together some interviews. Thanks again. Keep observing, because apparently the universe is taking notes.